Hello, guys. Welcome back to MedZone African Motives. We are still on our N6, and this is power machines. And okay, we just want to check this question, which is on nozzles, and that is April 2023 on nozzles. Okay, let us see what we have here. It's approximate, that is 20 marks. Yeah, everything here is actually 20 marks, as we can, as we understand. Most of our questions, depending with the layout that you are given. And now we also have this condition of answering. Sometimes it depends. They might give you to answer any 5 questions provided on the questions that you be given. So with time, we're just going to try by all means to just answer, like to have everything on your syllabus, so that you'll be able to choose according to the questions that you understand. But this one, it's one of the easiest topics, not to say easiest, but you can understand this as we are moving. Okay, let us have our questions quickly without wasting time. We are given, this was question 2, and that is a convergent divergent nozzle. He has got 93% of isotropically dry steam. So this is isotropically dry steam at a pressure of 400 kilopascal. Okay, this is it about the nozzles. If we are to check here, we are talking about dry steam. So we are talking about the flow of what? The flow of steam. A nozzle can be used for air. Okay, we can have it as a gas. Okay, or we can have it for steam. So this one, it is used for steam flow, meaning to say you are supposed to go back to your N5, revise everything about the steam. Okay, before we talk about the nozzle on its own, we have to understand the properties of what? Of steam. Okay, so I'm gonna explain and also have a recap of our N5 as well. So here, take note, it's a convergent what? Divergent. So when it is a convergent divergent like that, of which that's the most case that you are going to have in your syllabus, we are going to have something of this nature. Let us just have just a sketch of a convergent divergent. So you're gonna have something of this nature. All right. So this is what we are going to have when it is what? A combination of a convergent divergent. So in this case, we got at the critical values. This is your inlet. All right. So this is our inlet, as we know. We've got our inlet this side, and we also have our outlet on this side. All right. So at this condition, this is our throat, whereby we've got critical values at that point, which is the throat. All right. So this is where we have got the critical values here. That is where we have got the what? The critical values. All right. So the question is, what are we given? This is for a steam. So when it is for a steam, in this case, I want us to check what is entering here. We are given that it is 93% of isotropically dry steam at a pressure of, which is at this inlet. Take note. At a pressure of, meaning to say at the inlet. When the pressure is what? 400 kilopascals. At the inlet, this is the pressure entering this one. We've got the inlet pressure. That is where we have the steam as what? As dry steam. Take note, guys, here. Okay? It is entering as a dry steam. Okay? So this is what is happening here. It is entering as what? As dry steam. So this steam here is dry. Okay. Then, all right, we've got this part here where the steam flows through the rate of, at the entry, the steam is, all right, this part of the velocity, all right, then is superheated but loses this 125 kilojoules per kg of its enthalpy up to the throat. All right, take note. It loses this when it is superheated. Meaning to say, when it is reaching the throat, it is now what? Superheated. Take note what is happening there. When it is reaching the throat, it is now superheated steam. So here we are talking about the superheated steam. Let's just, we're gonna have something clear here. It's superheated. All right. Then the other thing that you're supposed to consider, then the pressure drops, this and that. Okay. At the throat, the steam has got a specific heat capacity because we know that once we've got the superheated steam, this is going to be the specific heat capacity of what? Of the superheated steam. All right. Then the divergent section of the nozzle has got efficiency of this when it is an index of 1,3. All right, we're going to take the information later on. But what is going to happen is that at the exit, we are going to have this now as the wet steam. All right, when it comes out here, it's going to be wet. So here we're going to have the wet steam. All right, so that is the idea that we have there. So you can just have our conditions. Remember, the inlet, it's 1. The outlet is represented by 2. And at the critical point, you just use C. At the throat, you just indicate with what? With C. So we can take the information. All right, let's just take the information, okay? We've got what? The efficiency here. Efficiency of 88%. All right, so you've got the efficiency there, 88%. What else? Sorry, this is 93%, 93%. So where am I getting the this one? This one is 93%. The 88 is the one that is at the end. All right. This is 93%. So when you are given this way, all right, when you are given this way, when they are saying the nozzle has got 93% of acetropically dry steam, that is, we've got the dryness fraction there. Remember, when the steam is dry and you're given 90% of it being dry, that is your dryness fraction there. So this is not efficiency. This is our dryness fraction, 0.93. Like I said, the dryness part is the one that you're going to have here at the inlet. And what else do we have? The pressure there being what? The pressure being 400 kilopascal. So we've got the pressure of 400 kilopascal when it is dry. All right, 400 kilopascal. And the steam now is, all right, take note about this one. This is the rate. The steam flows through at a rate of 481.52 kilograms per meter. So this is the rate of the flow. So we're going to give this the rate of flow as we are given this as the mass. This is 481.52 kilograms per minute. All right, so we shall see where it is used and how we are going to use this. Is it per minute or per second? Then at entry, the steam with negligible velocity. All right. So at the entry there, the steam has got what? Negligible velocity, meaning to say the velocity here at the end. Negligible means we do not, it's like it's neglected. Yeah, we are neglecting that. It's not counted. All right. So meaning to say the inlet velocity here is at what? At 0 meters per second. Remember C for velocity. So inlet, that's C1. Okay. Then we also have this here that it is superheated but loses here 125 kilojoules per kg of its enthalpy. Up to the throat, it's a loss. Okay. If remember enthalpy, guys, we are starting here. This is what they're trying to say here. This is the point 1. Okay. This is the point C. Remember, at the critical values, we said here we're going to use C. So here we are supposed to have the enthalpy, which is H1 for the dry steam. Then HC, which represents the superheated steam. But they are saying there is a loss here. From this to here, we have a loss from that point up to the throat. There is a loss up to the throat. understand the information, because you won't be given information like this on another question. But that idea of taking this information is the same that you use to answer even any other question. So there we are given the change that is happening on the enthalpy. Remember, enthalpy represented by H. So meaning to say H1 minus HC, because we are starting from what? The inlet up to the throat. It's not up to the outlet. It's taken here up to the throat. So they are saying H1 minus HC, which is the loss that happened, the difference, all right, is of what? 125 kilojoules per watt per kg. This is what they're giving you. So we are simply talking about the change in enthalpy that happened from 1 to 2. All right. So there we have got the change in enthalpy, which is the loss in this case. All right. So you can just save the change in enthalpy, which is from H1 to HC, because there can be a change in enthalpy from H1 to H2, but this one is up to the what? Up to the throat. So we are given this as 125 kilojoules per watt per kg. That is what we are gonna have here. Okay. Then let us move on. Then here we are given that where the pressure drops to what? To 1,200 kilopascal. All right. Where the pressure is going to drop to 1,200 at the what? At the throat. That is where the temperature. So this is the temperature, the pressure that we're going to have at the throat, PC, 1,200 kilopascal. All right. What else? All right. Let's see. I thought we're going to not take much time, but I see there's a lot there. All right. Anyways, let's move on. At the throat, the steam has got what? A specific heat capacity of at the throat. Why are we given the specific heat capacity? I told you guys, according to this information, that at the throat, that is where our steam is what? Is superheated. So that's why we are given the specific heat capacity. So this is the specific heat capacity of the superheated steam. 2.34 kilojoules per watt per kg Kelvin. All right, this is what we have. So we got the specific heat capacity in this case at the point C, that is at the throat. So this is happening at the throat, because that's where the steam is what? Is being superheated. So we're given this as 2.34 kilojoules per watt per kg Kelvin. All right, that is what we are given in that case. All right, according to our information, this is it. But if we take here, it's supposed to be per degree Celsius, because our temperature is going to be taken per what? We're going to use our temperature in degrees Celsius. All right, but anyways, does not affect. And here we are given that, and a temperature of where, when we are having this specific heat capacity, that's where we have this temperature. Since it is per kilogram Kelvin, meaning to say we're going to have this temperature in Kelvin in our presentation here as 192 at the throat. Remember, we are still at the throat. So this is the temperature of the throat. Remember, at the throat. So this will be TC at the throat. So the temperature there is what? 192 degrees Celsius. All right. Whereby if you add to convert to Kelvins, that will be 465 if you add 273 Kelvin. But this here, it's going to depend, where are you going to use this temperature in Kelvins? All right. If we are to consider the specific heat capacity here, like I said, this one, if we are to consider this, we are supposed to have this as per kilogram degrees Celsius, not per Kelvin. Because when we use the specific heat capacity, this temperature at the throat is the temperature that is corresponding when our steam is being what? Superheated. Guys, remember what we said at the throat. The steam is what? Superheated there. So HC is for the superheated. So meaning to say CP is the specific heat capacity for the superheated steam. And this is the temperature for the what? For the superheated steam. So this is going to be temperature for the superheated steam, which is 192 degrees Celsius at when this is taken per what? Per kilogram degree Celsius, because that is what we're gonna, when you use this, remember guys, from our steam, okay, when we are substituting the temperature, even from our steam table, we have what? Degrees there, degrees Celsius, not kelvins. So that's why this is supposed to be per kilogram degrees Celsius. All right. So please take note about that. Then this is another thing that we also have. The divergent section of the nozzle has got an efficiency of 88%. The divergent part. All right. It has an efficiency of what? Of 88%. When we are talking about the divergent, what are we referring to? That is the question. All right, because there we are given the efficiency, which is fine. But when you're talking about the divergent, which part are we talking about? Because this is a convergent divergent. So the convergent divergent, meaning to say, for the first part of the convergent, then the part of the divergent here. So the efficiency is affecting the divergent part. I just hope we are together, guys. The efficiency is affecting what? The divergent part. That is the one that we're given. So meaning to say, this efficiency that we are given is for stage 1 to 2. I just hope we are together there. Efficiency of 88%. This is affecting the stage, not the stage 1 to 2, but the stage of what? This stage of the divergent from C to 2, from the critical point up to the outlet. That is the divergent part. So this is affecting the stage C to 2. All right. That is the stage being affected there. Okay. Then what else are we given? I think that's it. Yes. All right. The other part here is the superheat index is. All right. So you've got the index there, the superheated index N, which is what? 1,3. So that is N for the superheated steam, which is 1,3. So remember, this goes with the superheated steam. It goes together whenever the steam is what? Is being superheated. This goes together with the superheated steam. All right. So what we are going to do is to attempt our questions and see how we are supposed to have these questions with our formula sheet also, so that you'll be able to analyze as an individual how the formulas are given from your formula sheet and how do you actually utilize or use your formula sheet in answering of these questions. All right, so let us check the first part, which is on what? On 2.1, because they want us to also use what? The steam tables. Take note, use what? The steam tables there. Okay, so if we take a closer look here on 2.1, we are supposed to use what? The steam tables and calculate one, the specific enthalpy and the velocity in meters per second at the what? At the throat. We need the specific enthalpy there and also the velocity. Okay, let's start with the specific enthalpy, which is, so what is important, like I was saying, is that you have to understand, because this is steam, all right? It's different from that of when you're dealing with a gas, when you're considering a gas. When you're dealing with steam, you have to be very careful. All right, so we have got the dry steam, the superheated steam, and the wet steam. So the enthalpy that we need here is for what? Is for the superheated steam. So how do you calculate the suppose that's HC? So our HC, the one that we want here, is for the superheated steam. All right, I can just even utilize this side here, no problem. So that's 2.1. So you are supposed to calculate HC, which is the enthalpy. But like I said, it's for the superheated steam. So this HC is equal to the HS for the what? For the superheated steam, which is H sup. If we check from your formula sheet on page number 1, we've got the formula for H sup, which is given as HG. It's given like this: HG plus CP into T sup like this minus TS like this. Okay. This is the formula that we're given. We also had this formula from our N5 on calculating what? enthalpy for the superheated steam. So that is the one that represents what? Your HC, which is what? At the throat. So you have to consider what type of steam is there, all right? And also, as we know that from this formula, this Hg that we are given and this Ts here that we are given are supposed to be taken at a certain pressure. And what is that pressure? At the what? At the throat. At the throat, we've got the pressure here, PC at the throat. We said it's what? 1,200 kilopascal at the throat. This is the pressure that we are supposed to use there. So meaning to say these are taken at what? At 1,200 kilopascals. That is at what? At the throat. So you're supposed to be careful with your information. As we know, this is the specific heat capacity at the superheated steam. This is T temperature of the superheated steam, the one that I wrote previously as TSS. If you still remember here, we talked about the temperature at the throat. That is the temperature of the superheated steam at the what? At the throat. Okay, so that one, we're just gonna need our steam tables in order for us to have Hg at 1,200 kilopascal and the superheat, the temperature, the saturation temperature at the same pressure of what? Of 1,200 kilopascal. So you're gonna need your steam tables. Let's check here. On our steam tables at 1,200. All right, so this is what we have here. For the pressure, remember our pressure is supposed to be at 1,200. So under 1,200, this is the part that I want here, under 1,200. All right. Okay, up to this. Okay, so this is at the pressure of 1,200 here. Remember what we need? We need the saturation temperature, Ts, and Hg for the dry steam, this one. So the saturation temperature there is what? 188. So this is our temperature, 188 degrees Celsius. And you also take the value of Hg down here. The value of Hg is going to correspond at this value here, which is 2,782. This is measured in what? Kilojoules per what? Per kilogram. Kilojoules per kilogram. So these are the values that we want. All right. So we've got our saturation temperature in degrees Celsius and our Hg. All right, so let us bring these values. All right, sorry for that. Okay, so here, remember we said our saturation temperature at 1,200 kilopascal. Our temperature there was what? 188,0 degrees Celsius, and Hg there was given as 2,782 kilojoules per what? Per kilogram. So that is the idea of the question. All right, so there we're just going to substitute Hc, which is our superheated, for the superheated steam, which is the enthalpy of the superheated steam. We're going to have Hg, which is 2,782 plus, remember, the specific heat capacity here is what? That is 2,34 kilojoules. All right, so this is 2,34. So there we're gonna use as it is 2,34. All right, into the superheated temperature. T sup there is what? 192, which is our superheated steam. That's 192 in degrees Celsius, because this one is also degrees Celsius. Ts, which is our saturation temperature, there is what? 188,0, which is just 188, like that. All right, so that was going to give us the value of Hc, which is 2,791,36 kilojoules per what? Per kilogram. So this is what you're going to have. All right, so you have to be very, very careful with your information, and also how to take the information from your information sheet and also your steam tables. All right, that's why we are told here to use what? To use the steam tables. It's a nozzle for steam flow. So we have to use the steam tables. All right. Then the velocity at the throat. All right. So the velocity at the throat, this one, we're not going to waste much time. I'm just going to bring you guys to your formula sheet. I also want you guys to be used to your formula sheet. If you check So this is our formula sheet here. We have got the velocities. Remember, we want at the throat. So what you're gonna have is that we have got two formulas here. This one for CC, that is the velocity at the throat, and also this one, the velocity at the throat. All right. So this you use it. This one where you are given the temperatures like this is the one that you use when you are dealing with what? With a gas. When it is for a gas, you're going to use this one when you're dealing with what? With a gas. All right. But if you're dealing with a steam, for steam, this is the formula that you're going to use whereby you are applying what? The enthalpies in this case. All right. So that is the formula that you're going to apply or to use. So like I said, guys, I want you to be used to your formula sheet. All right. So we're going to take this formula, like I said, so meaning to say, in order for us to calculate the velocity. Remember, that was the second question, to calculate what? The velocity. So the velocity, like we saw from that formula, is given as the square root of 2 times 10. Sorry for that. You see this software, guys. 2 times 10 to the exponent of 3 into h1 minus hc. So that was h1 minus hc. So make sure you also check the formula properly, plus c1 squared. Okay, so this is our formula. And we were told that C1, which is the inlet velocity, is what? Is negligible. We are not using this. We are neglecting this. It's not part of our velocity. It's a zero, that one. So this one, we are not going to consider it, just a zero there. And we also have what else here? Okay, if we check on this one, we said this one is equal to 0, which is fine. So C1 is equal to, this is no longer there. But what about H1? Do we have the inlet? Do we have here for the dry steam? Because we are considering H1 when the steam is dry. All right. So this part we do not have. But what we have is that this difference between H1 and HC, this one, H1 minus HC, we talked about it before. I want us to get back to this one. If we take a closer look here, we talked about this properly. All right. Okay, sorry for that, guys. You know, this software is like I was saying. But if we are to check here, we have got this here, the difference that we talked about previously. If you still remember, H1 minus HC is 125 kilojoules per watt per kilogram. All right, so that means we are going to take that. We have the difference already. This is the one that is indicated here. We talked about this. This is the difference in enthalpy that we had before. So meaning to say, we are just going to substitute the value that we already have in this case. All right. So that means here we're going to have our velocity, C as the square root of 2 times 10 to the exponent of 3 times this value as it is. All right. So the 10 to the exponent of 3 is for removing what? For removing the kilojoules. So you just write as it is as 125. All right. Like we said here, the velocity, the inlet velocity is a 0. So that's 0 squared, meaning to say there's nothing there. All right. So that is, we are going to have the velocity, and that was going to give you something like 500. All right. 500. Remember, this is velocity measured in what? In meters per second. So this is the velocity that we have at the throat. All right. So we've got the velocity at the throat in this case. All right. We might need this information. So let me just write it because I need that space there, guys. So we've got the velocity at the throat. We said it's 500 meters per second. We also have HC, which is 2791,36 kilojoules per watt per kilogram. All right, so these ones, we have them. I'm just going to use this space so that I do not take you guys away from the information. I want you to properly see the information that we have, and this can help us. And also, this we might need it, but I just hope you have the values with you guys. You can even rewind so that you can see the values whenever we need them. All right. 2.3, they are asking us to calculate the specific volume at the throat. At the throat. We are still at the throat. Give the answer correct to 4 decimal places at the throat. Okay. Guys, let us be together here. What is it about the throat? At the throat, the steam is what? Is superheated. So what type of specific volume is that? It is the volume for the superheated steam. This is V soup. All right. That's question 2.2. Remember from our N5, we've got the formula for V soup. All right, which is for the superheated steam. All right. If you check from your formula sheet on page number 1, supposed to be, let me just check your formula sheet so that I will be together. If you check from your formula sheet on page number 2, actually, it's given like this. V soup is equal to N minus 1 over N like this into H soup minus 1941 of everything over P soup. Okay. This is for the superheated steam. So as we are referring about the superheated steam, which is fine, which is happening where? At the throat. So meaning to say here, the volume that we shall have at the throat written as a VC is going to be equal to N minus 1 over N like that. Yes, you can use it like that, guys, or you can even write it proper like N minus 1 over N like this. All right, into the enthalpy that we have there when the steam is being superheated. Which enthalpy is that? That was HC here at the throat. That is where we have got the superheated steam. So this H soup that we are talking about is the same H soup that we calculated before, which is our HC. All right, so we are simply having what? HC there. What about PC, this one? What about this P soup, this one? What is it representing? That is the pressure that we have when our steam is being superheated, which is the pressure at the throat, which is our PC. So that's the idea there. So you see, it's just, that's why I said you have to revise your steam calculations from your N5, because it's an application now. You are now applying what you did previously. It's an application this time. All right, so we've got everything. Yes, just have to substitute N, which is our N. Remember, our index of superheated steam is 1,3. So that's 1,3 minus 1 over 1,3 into H soup, which is our HC. In this case, the one that we calculated as our superheated and the enthalpy for the superheated steam, 2791,36 minus 1941. That is everything over the pressure, which is our superheated, the one when the steam is being superheated. But this we are referring as what? As PC, which is 1,200 kilopascal. So that was going to give us the volume. As we are given, it is to 4 decimal places. All right. So on your calculator, you can even round off to 4 decimal places. I talked about this from our previous classes. But just for the sake of revision and for those who do not know how to round off on a calculator, let me show you the screen of the calculator here. All right. So this is it. I'm just going to insert my values here so that we can have them together. All right. There are 2 calculators. Why? Just need one here. All right. So let us have our fraction. Here we've got another fraction. Is that so? That's 1,3 minus 1, everything over 1,3 like this. All right. So we're going to have the bracket into 2791,36 like this minus 1941. All right, then we're going to divide to 1,200. So this is what you're supposed to have in actual sense. 0,81. All right, why is this? This value is not the same as the value that I had there. Is it? I missed something here. Minus 1,8. Where am I getting this 1,8? This is 1,9, not 8 here, 9. Because I'm getting different answer there. All right. So this is what you're supposed to get exactly. This one, 0,1635 like that. So in order for you to round off, if you do not understand this, you can use a calculator shift, then set up, you go to the fix here, which is 6. Then to 4 decimal places, you just press 4. So your answer will be rounded to 4 decimal places, which is 0.1635. All right, so this is 0.1635. Direct like that. This is volume, guys, which is measured in what? Cubic units, which is cubic meters. All right, so that is how we can simply round off on our calculator. So this is the volume when our steam is being what? Superheated at the throat. So we've got VC here, which is 0.1635 cubic meters. We might need this, you never know. All right, so let us see another question. But as you can see, guys, they're straightforward question if you understand the steam calculations from N5, because it's just an application, but something that is straightforward because the formulas, you know them, you are given. Then now they're saying the specific isotropic enthalpy. So when you're talking about this, we are referring to a condition whereby we are saying there is the exact value. There is the exact value. All right. Then there is the isotropic value, which is not the actual value of what we have. So these are the values that are presented with a bar like this. It is H2 bar like that, or it can be T bar like that. It's something of that nature. Those are what? Isotropic values. So now here they want you to calculate the specific isotropic enthalpy, the specific actual, take note here. This is the actual. The actual now. This one is not the actual value. This is the actual enthalpy. All right. And also the actual dryness fraction of the steam at the exit. Why are they talking about the dryness fraction at the exit? Because here, take note, we said at the exit, the steam is what? Is wet. And we know that if we're ever talking about the steam which is wet, there's a dryness fraction which is to be considered there. All right. When the steam is what? Is wet. There's a dryness fraction to be considered. All right. But this we are referring to the what? What are we referring to? To the dryness fraction. That is for the what? For the wet steam. So the question was, all right, how are we going to calculate the specific isotropic enthalpy? All right, so this is given as, that's 2.3. All right, so let us have this here. All right, so for the specific isotropic value, which is the enthalpy, which is given as H bar 2 like this. Remember, this is for wet steam. Remember, how do you calculate H wet? H wet is equal to HF plus X HFG. Remember, that's how you calculate your HF. Your H wet, I mean, from your steam. Because this steam is wet. So meaning this is going to be given. So the formula when you are calculating for the wet steam at the exit, this will be HF plus X. And our X in this case is the one that we have from the stage of what? From the stage of the critical to the outlet on the divergent part. So we are going to use XC there, all right? Times what? HFG. So that is what we have in this case. And also the other thing, the pressure that we have there is which pressure that we are given. Take note here, we are given that when we have got this dryness fraction of 0.93, the pressure there is what? It's 400. So the dryness fraction that we are given here, in this case, we've got the dryness fraction and the pressure, it goes with this pressure. All right, so you can just even write normally the way that you just write your formula X, HFG, so that you do not have a confusion. Remember, this is the pressure that is with this dryness fraction. So meaning to say, whenever we are to use this dryness fraction, the pressure is supposed to be at what? At 400 kilopascal. So what do we need at 400 kilopascal? We need HF and also HFG. So these are the two that we're going to need there. All right. So we need our formula sheet. Our steam table. So let us get back to our steam tables, guys, at 400 kilopascal. That's here. All right. Where's that value? Here. So if we are to check on this one, oh, no, I need this page. Sorry for that. I need the other page. Okay, this one, no problem. So this is the one that I need here, at 400. All right. So that is at 400. This is what we need. This line here, straight at 400. So at 400, we're gonna need the value of HF there, which is the value of HF at 400, and also HFG at 400. All right. So that is our HF in this case here is 605. And HFG is what? 2138. All right, 2133. All right, so these are the values that we are going to need. Only these ones. So you just need your steam table there. All right, I think something that was direct there. Okay, so meaning to say at 400, we're gonna have this. Okay, guys, I think this has to do with network or something. Why is it? Okay. I just hope we're gonna be able to finish. This video is now too long. Maybe that's why. All right, no problem. So I'm saying that at 400 kilopascal, our HF was what? 605. All right, we might need this value. So let me just write it. 605 kilojoule per watt per kg. Then HFG there was 2133. Kilojoule per kg also. So here we're just inserting our values. HF 605 plus the dryness fraction, that's 0.93. All right, times HFG, which is 2133. All right, so that is what you're gonna have in this case. And this is gonna give us 25, that's 2588.69 kilojoule per kg. All right. So remember, this is the enthalpy then. All right. Then what about the specific enthalpy now? So for the specific enthalpy, we can take advantage since we have the specific isentropic. We can have, I mean, for the actual now, in order to calculate the actual enthalpy, we can take advantage of what we have also, because remember, we also have the efficiency of this section, which is the efficiency of what? Of 88%. Remember, the efficiency is for the divergent from C to what? To 2, when it is what? On the divergent. So we can take advantage of that efficiency. If we check here, just hope I inserted the formulas for the efficiency. All right. I just hope I inserted those formulas, guys. No problem. Let me just check. All right. So these are the formulas here. We have the formulas for the efficiency. So if you are to take a closer look on these formulas that are affecting efficiency, we can see that there is a condition, because as we are focusing with the stage of what? From the critical to the outlet. So we need the efficiency that is affecting this, which is this part. Critical up to the outlet, this one. This is the best formula to use. We can't use this one because this one is for 1 up to 2, the convergent part. As we're talking about what? The divergent part, that is where we have the efficiency. All right, from C up to the stage 2. So this is the formula that is best that I'm going to take. All right, so with this formula, I want us to have it here and see how to apply these formulas in order for us to find H2. So we saw that from there, our efficiency was given as what? As HC minus H2 over HC minus H2 bar, which is, in this case, remember what to calculate H2. So you can just substitute everything. HC, we have it. We calculated our HC before. So you can even make this the subject. Let us just try to make it the subject here. Okay. Let us go back to our mathematics. We're going to cross multiply. So it's efficiency into HC minus H2 bar is equal to, all right. Why is it that, all right, it's because I was trying to indicate here. Now it's like a bar here. It's not a bar. This is HC minus H2. Remember, we want to calculate H2. So you can transpose H2 this side it becomes a positive. So H2 is equal to, we remain with HC minus the efficiency into HC minus H2 bar like this. Okay. So we have made H2 the subject. So this is from your mathematics, guys, change of subject. So HC, we calculated this before. So it's just a matter of substitution. HC, we had 2791, this and that, all right? So you're going to substitute our value. In this case, that will be 2791, 36 minus the efficiency on the stage 2 to C to what? C to 2. This is the stage 2, C to 2. The efficiency there is 88% as a decimal. That's 0.88 for the divergent stage. Then HC, we just a substitute again. It's just a repetition of this one that we substitute 2791,36 minus the isotropic value that we got here previously, which is what? 2588,69. So that is how you're going to calculate your H2. So that is how we can play around with this information. And our H2 there was going to be 2613,010204. So it's going to be a 0 there, kilojoules per kg. This is now the actual value. All right, this is now the actual value. The actual value. So you must be very, very careful there. All right, then what else do they want on the same information? Remember, they said here, the actual dryness fraction at the exit again, at this point of the exit. All right, the actual dryness fraction, how do you calculate it? All right, remember what I said about this, to say here, H2 is taken from H wet because the steam there is wet. And at the exit, the steam is wet. So meaning to say we are now using H2, which is the actual value. This was the isotropic value. Now we are using H2, which is the actual value. So H2 is equal to HF, all right, plus what? The X, which is our dryness fraction. This was the X that we had at the critical condition. From that one that we are given at, at a pressure of 400. But this one is going to be the actual, the one they want here. So it's going to be X actual. So this is the actual dryness fraction at the exit, then times HFG. So this condition is not going to change. All right. This condition is not going to change. So we need to calculate the actual value here. So how are we going to find it? Just going to make it the subject. Transpose HF that side. So it's going to be H2 minus HF. Then we divide by HFG because we want to remain with what? The actual value. So you're going to divide by HFG. This is X actual. So that means the actual dryness fraction in this case is going to be equal to H2, which is the actual enthalpy in this case at the exit. What is our H2? We calculated here our H2. So as you can see, guys, it's just a substitution part here. So it's just going to substitute H2 minus HF. So this is H2 2613,01 minus HF. HF, remember when we took at 400, at that pressure here at 400, our HF was what? 605. So that one is not going to change. We are still at 605. And also HFG at that pressure of 400, it was what? It was 2133. So there is just a matter of what? Substituting and finding the actual what? Dryness fraction. So the actual dryness fraction was going to give us 0.941 to 3 decimal places if you round off properly. All right. So that was it in this case. Okay. Then the other part here they want is the steam volume flow rate. All right. The steam volume flow rate at the exit in cubic meters per second at the exit. All right. This is at the exit, and we need the flow rate. How can we calculate the flow rate? All right, let me use this one. I don't think we're going to use this, but if we need it, then we just have to recall, guys. All right. Let me just write something here. Remember, at the exit, that is the point 2 here at the exit. This is the condition of 2. But there, we need the flow rate, the volume. So in order for you to have the volume of the flow rate and it's supposed to be cubic meters per second, it means there's something that is happening here. There's something that is happening here. In order for us to have this volume in cubic meters per second, what does it mean? All right. The flow rate is going to be given as the mass, which is the mass per second for us to have the volume per second, times the given volume at the exit. So if we take a closer look about the volume at the exit, from our formula sheet, we're going to see that from our steam tables, that volume will be given in cubic meters per kilogram, like this. It will be given in cubic meters per kilogram. That's why I'm talking about involving the mass, so that we can be able to cancel, because remember, our mass, as it is given here, it's kilograms per minute. So in order for us to have per second, we shall have our mass in kilogram per what? Per second, times the volume, which is measured in cubic meters per what? Per kilogram. So this kilogram and kilogram will cancel. You remain with the cubic meters per what? Per second. So that's how you can obtain the cubic meters per second. So it means we must have, or we are supposed to have the mass in kilograms per second, of which the mass is already there. So you just have to convert per second. So where do we have this volume, which is measured in cubic meters per what? Per kilogram. Where do we have this? This is the volume at the exit. The volume at the exit. So how do you calculate the volume first at the exit, which is our V2? All right. So at the exit, the volume, which is V2, at the exit. At the exit. This is the volume of what? Of wet steam. So we are calculating V wet. So V2 is equal to V wet. Remember how do you calculate V wet? V wet is simply the dryness fraction times what? Times the volume of the dry steam, which is Vg. So here we are talking about V2, which is the actual volume. So this X is supposed to be the actual dryness fraction at the exit. Where the dryness fraction is involved here, we said it's involved at a pressure of what? At a pressure of 400 kilopascal. So meaning to say this Vg is the volume at what? At 400 kilopascal. So this is going to give us V2, which is the volume, in this case, this one. Okay? So that means the volume, which is our V2 at the exit, is going to be the actual dryness fraction. We calculated this and we still have it. The actual dryness fraction, we got 0.941. All right. So this is what you're going to do. Just like the same way we took those values for HF, and we are going to do the same thing for VG at a pressure of what? 400 kilopascal. Okay, let me just show you guys from the steam table here. This is at 400. So we want the value of Vg. This is where we have Vg. Like I was saying, the Vg, it's cubic meters per kilogram. So that's why we have to remove that, because we have to cancel per kilogram. So the Vg there at this pressure is what? It's 0.4622. All right, that is our Vg there. Okay. So meaning to say here, we are going to take our Vg. It was given as 0.4622, 0.4622. Like I said, this is in kilograms per cubic what? Per cubic meter in, volume, volume, it's cubic meters per what? Per kilogram. So meaning to say, the volume that we are going to get here is going to be in cubic meters per kilogram. So if you multiply this, you are going to get 0.435, something like that, to 3 decimal places, which is in cubic meters per what? Per kilogram. Okay. So that's why I said, in order for you to calculate the flow rate, which is this one, all right, which is our flow rate, this one, in cubic meters per second, we have to cancel by what? By the mass, which is in kilograms, because the mass is the only part that has got kilograms. But that mass is supposed to be in kilograms per what? Per second. So we are now using our formula, mass times what? Volume. So it's going to be mass times V2. So the mass in kilogram per second is going to be what? So the volume, the flow rate is going to be the mass per second, which is 481.52. Per second, we divide by 60 because this is per minute. All right? Per second. Or if you want, you can just divide direct, which is going to give you something like 8,025, like that, which will be in what? Kilograms per second. So if we multiply this to the volume now, which is our V2, the actual volume of 0.435, which is measured in cubic meters per kilogram, you will see that per kilogram and this kilogram will cancel. You remain with the meters on top. The second, which is in the denominator, as you can see, the cubic meters is on top. So that's the volume. It's going to be in cubic meters, 3,491, something like that, cubic meters per what? Per second. The second is in the denominator, so it means per what? Per second. So this is what? The volume flow rate. Volume flow rate. So in order for you to have the volume flow rate, take a closer look, or the a closer look on the units there. The mass times the volume. But the mass is supposed to be not, because they might ask this in cubic meters per minute. If it is cubic meters per minute, that means I have to use the mass in cubic meters per minute as it is. But there it was cubic meters per second. So it means something, there's a part that has to be per second in order for our answer to be also per second. That is the idea there. All right. Then another question, they're asking us here to draw a labeled, and this is entropy diagram. So we've got the enthalpy and entropy diagram, and indicate any three values on the diagram, for the enthalpy entropy. All right, so let us just try to have a sketch of this here. Our enthalpy entropy diagram is supposed to be of this nature. I'm just going to have a sketch. I just hope you still remember some of the values, because we're going to need some of the values that we calculated before, since we're talking about the enthalpy. We calculated our enthalpy is there. All right, no problem. Let me just show you guys a sketch of this. So on enthalpy entropy diagram, all right, so this is 2.5. We are dealing with what? An enthalpy entropy diagram. All right, so we're gonna have the vertical and horizontal axis. In this case, the horizontal axis is the one that represents your entropy. In this case, remember, entropy is S, which is measured in kilograms per kilogram Kelvin. Okay. Then on this side, we're gonna have the enthalpy, which is H. Remember, enthalpy is what? Is H. And our H is measured in what? Kilojoules per what? Per kilogram. Okay. So what happens is that your values, they are affected from the inlet when we have got the dry steam, the critical values when the steam is superheated, and the outlet when the steam is what? When the steam is wet. So this is what you're gonna have. You're gonna draw this here showing or corresponding to the enthalpies. corresponding like this. So I'm going to explain how the values are going to correspond to them. Just going to have a sketch. So at the point 1, this is representing 1. So we've got pressure 1. This is the critical. So we've got PC. And this is the outlet, which is P2. All right. So from 1, you go straight up to PC. You're going to go straight. Then at this condition, as you are maintaining straight, the value that corresponds there is for the isentropic value. So this, at this point, that is where we have our C for the critical value. But this will be for 2 for the isentropic value, not the actual value. The actual value is the one that will correspond this way. So this is where we have our 2. So be careful on that one. So meaning to say, we have got the enthalpies that are corresponding H here in kilojoule per kg. At the point 1, we say this will correspond here at point 1. So meaning to say, what we have there, we've got HC. So the value that you're going to have there is the value of what? HC there, when we have got 1. So this will be the value of HC. Remember our HC, we calculated our HC, guys. It was 2791.36 kilojoules. So that was the value of HC. Then at this condition, if we take at 2 here, it's going to be something above like this. That's at 2. So we're talking about H2. Remember H2, that was our H wet. We calculated H2 I think it's the one that we just calculated now. Now we've got a lot of values, guys, but I hope you still remember us calculating that value of what? Of H2. Now I've got a lot of information that I wrote here, but that is where we're talking about this H wet. If you still remember, maybe it's the one that I erased here. But that value of H2 was 2,613.01. Then remember, we had its isentropic value of H2. That was the first value that we calculated for H2 bar. And that was 2588.69. I just want you to also check those values properly. So this is happening at a pressure 2. All right, at a given pressure. So here we're going to have 2. Then this is for what? For the isentropic value. All right. So you just indicate something of this nature, you're going to have your full marks. All right. That is how you can have your what? Your entropy. That is our entropy diagram. All right. Our entropy diagram. Entropy in this case, kilojoules per kilogram Kelvin. Then the enthalpy in what? Kilojoules per kilogram. So we just hope we have similar questions on the steam, so that we can also try to apply the same information, and also to have a different question on the gas. When we are dealing with the gas, it can be a nozzle can be used for a gas purpose. So we want to see that type of a question, and how do you answer that type of a question as we prepare ourselves for exams ahead of time.